Hello, my name is Mark Height, and I'm going to guide you through my presentation, High Performance Simulation Framework for Geothermal Applications. Um, I will skip motivation part because essentially forward simulations are critically important if you want to improve your uncertainty quantification workflow or optimization workflow. I'll start my talk with describing CPU and GPU devices, which we essentially use to run computer models. Then I will talk about Delft Advanced Reservoir Terror Simulator, or DARTS. I'll explain how DARTS uses GPU, and we will get an answer to the question if a 100-year forecast for a 3D model of geological scale can be run in 9 minutes. Uh, I will finalize my talk with some conclusions. Let's go. CPU, or Central Processing Unit, is a square device which you can find in your desktop behind the radiator and ventilator. The main purpose of CPU is running operating system, drivers, and hundreds of various programs concurrently at the same time. On the plot on the right, you can see the history of almost 50 years of microprocessor data. We see how Moore law takes place. We see that from orange triangles. Moore's law tells us that the performance of CPU doubles every 2 years. And initially, it was thanks to increase of frequency which CPU worked on. But starting 2000s, the frequency raise was stopped because of the physical limitations. And later, more and more cores were introduced to CPU, which you need to employ in a special way if you want to use the full performance of your CPU. GPU is a graphics processing unit. It is a square device, not square, rectangular device behind, just below the CPU. Its main purpose basically is to generate the video signal and send it to your monitor. However, starting from 2000s, people were experimenting with offloading some computational tasks on GPU. GPU, the main purpose of GPU is running large workloads with a high level of concurrency. It has thousands of cores compared to tens of cores on CPU. Nowadays, it's hard to imagine that such problems as deep learning or mining of cryptocurrency are done without GPU. Not only because GPU are much faster for these problems than CPUs, but also because they are more energy efficient. In the top 500, the 500 fastest supercomputers in the world, the number of systems equipped with accelerator steadily grows and reaches almost 150 in the last year. If we compare performance of CPU and GPU directly, we could use two most important characteristics: peak double precision and peak memory bandwidth. Peak double precision tells how fast devices can crunch numbers, and peak memory bandwidth tells us how fast we can deliver those numbers from operating memory to the computational device. For problems such as reservoir simulation, peak memory bandwidth is even more important. However, both characteristics, they show quite an exciting difference between GPU and CPU, and the gap continues to increase. The plot in the bottom shows on the example of Echelon, which is a reservoir simulator which entirely runs on GPU. So the speed of Echelon, as shown, is fully proportional to memory bandwidth. So it's much more beneficial to use GPU for reservoir simulation problems, and it will be more and more important because the gap between GPU and CPU continues to increase over years. Delft Advanced Research Terra Simulator, or DARTS, is developed in Delft University of Technology. It is a Python package with high-performance extensions, which you can embed perfectly into existing optimization or uncertainty quantification workflow in Python. At the same time, it provides outstanding performance on both CPU and GPU. Reservoir simulation capabilities include full implicit scheme, which allows for unconditional stability. So we can run large time steps as big as 1 year for geothermal, for example. We run both on structured and unstructured grids. Discrete fracture models can be run using DARTS. And we employ accumulation, advection, diffusion, and reaction effects in various combinations for different kinds of applications, such as geothermal, hydrocarbon production, or CO2 sequestration, and many more. In particular, geothermal application for now includes 2 phases, water and steam, and a single water component. We use pressure enthalpy based formulation, and all the properties are computed externally using EAPWS library, specifically regions 1, 2, and 4. The key feature of DARTS is called operator-based linearization, or OBL. I will not describe in details how exactly it works. Instead, I will show an example how easily we can embed external library into property computations thanks to OBL. This is a piece of Python code where we import some routines from EAPWS library, and this is exactly a code which actually takes place into simulations which are running on CPU or GPU. So this class computes the temperature. We need to derive it from a certain interface and overload one single function, evaluate, which received a single parameter of state. The first element of state is pressure in bars. The second is enthalpy in kilojoules per kilomole. We convert these units into appropriate units and call backward one TPH routine from EAPWS 97 library directly. Instead, you of course can make your own implementation. The most important thing is that it will not affect the reservoir simulation performance a lot because and thanks to OBL feature. Now, in order to approach how we can actually use CPU, let's take a look at the simulation from very distant perspective. Basically, it's 3 loops, and on each iteration of non-linear solver loop includes Jacobian assembly, which takes 5 to 10% of time, and linear solver loop, which takes almost all the other time. Basically, these 2 operations take the entire simulation time for full implicit scheme. How one can use GPU? The simplest option is to take one specific operation like matrix vector multiplication and perform it on GPU. However, you will still need to deliver data from CPU to GPU in order to perform this operation. You need to send matrix and vector to GPU and take vector back. And you will have to wait until transfer is complete. Despite matrix vector itself can be improved 20 times, this waiting time kills all the benefits. More viable is option 2, where we put the entire linear solver loop on GPU. You can benefit a lot from this, but still you'll have to send some data from CPU to GPU, matrix and runtime side and solution, which limit the amount of benefit that you can get. This option is used by many, however, because it's simpler than the next option, option 3, where we keep almost everything on GPU, including the entire nonlinear solver loop, while CPU only initializes it and take control of the whole simulation. We still need to do data transfers, but first, they are much smaller than all previous cases, and second, they can be performed in a non-blocking transfer without penalizing the overall performance. In order to implement DARTS on GPU, we developed some parts ourselves, others we took from existing libraries. Let's take a look how it works. As example, we used a realistic geothermal model. It is very heterogeneous, so modeling on this geological scale makes a lot of sense. And here you can see how uneven and heterogeneous is the cold front after 100 years of simulation. For the test configuration, we took a gaming PC with a single very good CPU and top of the shelf gaming video card. We performed 3 simulation runs: sequential on CPU, multi-thread on CPU, and GPU runs, and compared the run times. Here you see the results. The sequential run took in total around 80 minutes. CPU multi-threaded version was able to bring the time down by a factor of around 2, while GPU performed the whole thing at less than 500 seconds or less than 9 minutes. So we got an answer on the question in the beginning. Now, relative comparison, we see that if we compare GPU over multi-threaded CPU, the most fair comparison, then the total difference is about, the total speedup is about 6. If we compare GPU over sequential CPU version, the total speedup is around 10, while linear solver, for example, is 13 times faster. At the same time, multi-threaded version on CPU can only improve it by a factor of 2 or 3. Takeaway. DARTS does offer unique GPU simulation capabilities for geothermal applications. Indeed, we can simulate a 100-year forecast using just a gaming GPU video card in less than 9 minutes. Still, some parts of DARTS were developed by us. Some are taken from libraries, so we indeed can improve all the different parts of GPU workflow. So the potential of GPU utilization is yet to be realized. If you are interested in this talk and in real applications of DARTS in different workflows, you can also take a look at other DARTS related talks on WGC 2020+1. You can use the submission number to search for the talk faster. I'd like to acknowledge Total Company, Huikao, and Arthur Ildashev for their help and support. And thank you for your attention. I look forward very much seeing you on my presentation at WGC 2020+1.